Hello, people. Welcome back. So let's go ahead and think back about what we've studied. In the first unit, we actually understood how to think about current and how to build a small mechanistic model of how electrons move through a metal or the atoms of a metal with a certain drift velocity and how to relate that to the current density and the electric field in the metal. Then in the next unit, we actually studied Ohm's law and we understood how to use Ohm's law to actually evaluate the resistance of an ohmic material. So that is already beginning to teach us many aspects um, of electrical circuits. And we also understood in the previous unit how to obtain the resistance of a resistor, which is to say that the resistance of a resistor is just equal to the um, the value of the potential drop across the resistor divided by the current flow in the resistor. Now it's time to go ahead and build some simple circuits and understand issues of power, energy, voltage, etc. in that circuit. So let's go ahead and look at this circuit that we see in the figure out here, and we understand already that um, the device on the left is indeed a battery. We've studied that already. And the device on the right is actually symbolically representative of a resistor. So what does a resistor do? It provides a certain resistance to the current flow. And so we show it as a sequence of bends or squiggles that kind of resist the current flow. So it's very nice and symbolic. Now let's go ahead and imagine that we have a certain amount of charge flowing through this circuit. So if I have an amount of charge flowing through this voltage rise in the battery, and let's say the amount of charge is delta Q, then we understand that the change in energy is just given by delta U, and that delta U is just equal to delta Q times the voltage delta V of the battery through which this charge is being driven. And because it's going from a lower potential out here on this negative plate to a higher potential out here on the positive plate, we have a voltage rise, and therefore we have a rise in potential energy of this charge as it goes through the battery in the conventional direction of current flow. With this, what we're interested in, oftentimes with electrical circuits, is not energy per se, but power. And power is just energy divided by time. So we can actually go ahead and divide this guy by time. So let the amount of energy spent be in an amount of time delta t, and that relates to the amount of charge flowing through the circuit in an amount of time delta t. Now notice that at this point we have something very useful because delta Q divided by delta T is nothing but the current. And so we realize that while the charge acquires some potential energy as it goes through the circuit, when it goes through the resistor, what's actually happening is that this energy is being dissipated in the resistor. And how much energy is being dissipated in the resistor? The answer is that the amount of energy being dissipated in the resistor is exactly equal to the amount of energy that is being supplied in the battery. Why is this energy being dissipated? The answer is that it's being dissipated because the electrons flowing through the resistor, and those electrons make a copious number of collisions with the atoms in the resistor, and in doing so, they can actually dissipate the energy in the and deliver that energy to the atoms and therefore heat up the resistor. So we actually see that we have a mechanistic model for how current flows, and we can now say that the amount of energy used up in the resistor is just equal to, so the amount of power dissipated in the resistor, which is the amount of energy divided by the amount of time, delta U divided by delta T, is just equal to delta Q divided by delta T times delta V, where delta V is the same voltage in the battery, which is actually across the ends of this resistor out here. So this is a very idealized, very simple circuit. We will make it a little more complicated as we go along. And so delta Q divided by delta T is just the current, and that gives us an expression for the amount of power dissipated in a resistor. Now, typically, You could have a resistor device which just is designed to dissipate power for whatever reason, but you could also have devices like a light bulb. A light bulb is a very good proxy for a resistor because when electrons flow through the light bulb, what they're doing is they're hitting the atoms in the filament of the light bulb, and in doing so they're exciting the atoms, and those atoms, when they de-excite, emit electromagnetic radiation, which is the light that we care for. So that gives us another example of a resistor. Likewise, an electric motor in its rudiments is a very good example of a resistor, because what it does is, by way of having current flow through the armature of the motor, it basically does work for us, and that work is electrical energy that we've turned into mechanical energy in the motor and that we can use. So we understand that resistor is in general a very broad concept. It basically pertains to any device that is actually drawing power out of a circuit, but we have to be a little more careful because there's the issue of how the power can be phased out of the circuit and so on and so forth. So at a very zeroth level, we can think of many devices that we connect across the outlet as being analogous to resistors. So let's then go ahead and understand that the power is in fact the rate at which energy is delivered to the resistor, and that is in fact the energy that is given back to us by the resistor in terms of some useful work. So for example, if you think about a typical resistor will get hot, and you will actually be able to experience that heat in the resistor, and eventually there'll be an equilibrium between the amount of heat that is being radiated into the atmosphere by the resistor and the amount of power that is being delivered to the resistor by the circuit. Now, if we think about a light bulb as another source of power, what is happening in an incandescent light bulb is that you have the energy of the electrons that are flowing in that incandescent filament being turned into energy. Now, many of us don't see any incandescent light bulbs anymore, but they're the light bulbs that were invented by Thomas Alva Edison. The problem with incandescent light bulbs is that they're only about 7% or 8% efficient, which means that if you have a 100-watt light bulb, it's actually giving you about 8 to 10 watts of real luminescent energy, and the rest of the energy is being dissipated as heat, which is in fact why, which actually explains why there's a strong movement towards compact fluorescent light bulbs and eventually towards LED light bulbs, because they have a higher efficiency. Namely, an LED light bulb typically will give you about 40 to 50% efficiency, so it gives you the equivalent of a 100-watt light bulb, but it actually goes ahead and uses about 20 to 30 watts to kind of give you that amount of luminescent energy. So an LED light bulb is in fact very efficient compared to um, uh, uh, an incandescent light bulb. So with that understanding, let's then go ahead and develop our knowledge. So we've already seen that the power dissipated in a resistor is just equal to I times delta V, but we know that R, the resistance, is equal to the voltage divided by the current. So we can actually say that delta V is equal to R times I, and therefore, if we stick that in here, we get another expression for the power dissipated in the resistor, which is equal to Ri squared. Or alternatively, if we can obtain an expression that is entirely in terms of the voltage across the resistor and get delta V squared divided by R. So all of these are equivalent, and all of these are measures of power, which is always measured in watts. Now, with that said, the battery is also doing something. And typically, and let's talk about an idealized battery first, and then we'll talk about a real battery. An idealized battery just gives you a constant rated voltage across its terminals. So let's call that a fancy little E. for the voltage across the terminal. We'll understand why E is actually referred to as an EMF later on. So that is why we call it a fancy little E. And we can actually go ahead and say that if you have a voltage difference given by this fancy E across the ends of the battery, and you have a current I flowing through the battery, then the power supplied by the battery is given by the rated voltage of the battery times the current. Now we will modify this as we improve our studies in the next subunit or subsection, but let's go ahead and continue with this idea. So, one of the things that is worth kind of reinforcing again is that the drift velocity of the electrons inside a circuit is typically amazingly tiny. However, it's the overall flow of current that matters, and realize that the current is not used up anywhere in the circuit. The current just goes around in the circuit. So with that, we come to this first thought question, which basically says that you have a 60-watt light bulb and a 100-watt light bulb. The question asked of us is, which of them has the larger resistance? Now, to keep this problem very, very simple, we can actually go ahead and say that the voltage that is delivered by the power outlet, by the outlet in our houses, is always a constant. It's 110 volts. And let's go ahead and keep it simple. Think of it as DC voltage for now. So we can actually go ahead and say that the power delivered by a 60-watt light bulb is just 60 watts. That's how much power is used up by the 60-watt light bulb. And that should be equal to the 110 volts squared. Let me go ahead and erase this and write it again. So we have 110 volts squared divided by the resistance of the 60-watt light bulb. The 100-watt light bulb, let's say it's highly efficient, fully efficient, it uses up 100 watts of power, and therefore it is equal to 110 volts squared divided by the resistance of the 100-watt light bulb. So we actually now begin to understand what is the issue out here. Namely, the question asked of us is, which light bulb has the higher resistance? Now realize that 100 is larger than 60, and therefore, now the numerator is the same because it's the same voltage that you apply to both the light bulbs. And therefore, since the numerator is the same, if 100 is larger than 60, then R100 should be in fact smaller than R60. So we come up with the realization that the resistance of the 100-watt light bulb should in fact be smaller than the resistance of the 60-watt light bulb. Okay? And so that's the idea behind this question, and that allows you to obtain the answer. Namely, it's the 60-watt light bulb that has the larger resistance. Okay, so with that, I will leave the second thought question to you. You can read it and think about it, and we'll have a chance to answer it in class. So with that, let's go ahead and take up a little more practical issue associated with electric transmission. Try to understand what makes for an efficient power grid. So to do that, we'll go ahead and take up a little compare and contrast between the situation as it prevails in the US and the situation as it prevails in Europe. In the US, our transmission lines actually transmit electricity at 500,000 volts. Now, of course, there's a system of transformers. Those are the beige boxes that you see in those little fenced off electrical areas which say do not enter. Those are the things that actually step that voltage down to a safe voltage so that in your house you're just dealing with 110 volts. And later on we'll have a chance to understand why it is a good idea to have just 110 volts coming to your house. Namely, it's very safe voltage. You're not likely to electrocute yourself if you touch that voltage. So the bottom line is, though, that in the US, these high tension lines which transmit power from the power stations to your home are actually rated as 500,000 volts. In Europe, the power lines, the high tension power lines, which transmit energy from the power stations to the homes of the people, are actually rated at 2 million volts. Let's understand which is better and why. Now, realize that the power is always equal to the voltage that you're supplying times the current that you're drawing. So if you have the same amount of power rushing through a US high tension line and a European high tension line, then if the European high tension line operates at a higher voltage, it will therefore be able to operate with a smaller current. In other words, to transfer the same amount of power, if you up the voltage, you can go ahead and reduce the current. Now, why is that a more desirable thing? The answer is that the resistance of the tension lines that you use is about the same. And the resistive losses in these tension lines go as R times I squared, which means that if you have high tension lines in Europe, which operate at 4 times the voltage of the high tension lines in the United States, they actually can carry the same amount of power while having a current that is 1/4 as large as the one that is carried in the American tension line, and therefore the resistive loss is significantly lowered in the European high tension line than in the American high tension line. So this gives you an idea of why it is beneficial to have a power grid in the United States that operates at a much higher voltage. And that is to some extent what the Obama administration was pushing for at one point. But this is actually just giving you a scientific view of how this mathematics works out, and you can make your own political decisions in your own way. So with that, let's go ahead and move on to the next transparency and the next section, which deals with understanding what happens with real batteries. Okay, so the reality is that anytime you talk for a long time on your cell phone, you're actually seeing that the back of your cell phone is getting warm, and what sits at the back of your cell phone is in fact a battery. So what happens is that because you've talked on the cell phone for a very long time, you're basically drawing a lot of current from the cell phone. And the reason the battery becomes warm is that as you draw a lot of current from the cell phone, a real battery is not just an idealized battery like the one shown out here, but rather a real battery is a combination of an idealized battery plus an internal resistance. And this internal resistance can in fact be non-negligible, and therefore there is some amount of energy being drained as you have current flow taking place in this internal resistance of the battery, which is why the battery heats up. Of course, the current also flows through the rest of the circuit, and hopefully the rest of the circuit is efficient. It will also heat up a little bit, but perhaps not as much. So with this understanding, we understand how to work with real batteries. Now we say that the battery is a source of electromotive force. Okay, we understand that electromotive force, unfortunately, is not any real force. It just turns out to be a very arcane use of a terminology that came before we understood all aspects of electricity and magnetism, and therefore we can actually say that the battery delivers an electromotive force, which is why we actually use this squiggly E to denote the electromotive force delivered by the battery. But what the electromotive force actually pertains to is the voltage, the promised maximum possible voltage delivered by the battery across its terminals. So now let's go ahead and make a very simple mechanistic example of a very simple situation where you have an idealized battery like this and a simple idealized resistor like this, and this is the resistor and this is the battery, and this battery has a certain voltage. What is actually happening as currents flow through this battery is illustrated by these two little diagrams at the bottom. So imagine, if you like, that current flows through the battery and it goes across the battery from the negative terminal to the positive terminal. That is very analogous to my hand going ahead and picking up a marble and raising it to a much higher potential energy and releasing the marble down the ramp. Now, the interesting thing is that the marble therefore got some potential energy as I raised it with my hand, and what the battery is doing is analogously, it is raising the charges that flow through it to a higher potential. Now, once these charges are put at a higher potential at the top of the ramp, you realize that this ramp has a lot of pegs uh, that have been hammered into it. And what these pegs are doing is every time the marble tries to roll downwards, the marble basically bumps into the peg, delivers all of its kinetic energy back to the peg, and then starts rolling back down again. Then it hits the next peg and delivers whatever kinetic energy it has acquired back to the peg, and then it starts rolling down again till it rolls down the ramp in this highly resisted formalism, or in this highly resisted format, which is why this situation serves as a good proxy of what is happening when current flows through the resistor. So you actually realize that current flowing through a resistor can be modeled as a whole bunch of pegs on a ramp which are basically obstructing the flow of these marbles. And in an analogous fashion, the electrons flowing in the circuit, but their easy and natural flow is being obstructed by the atoms inside the resistor, which continuously have collisions and therefore drain the energy from the electrons. So this is a good um, uh, uh, pictorial model for what is happening in a simple idealized battery. Now with that, we realize that what happens in a real battery is more likely shown out here. So you see that this dashed line actually shows us a real battery which can be modeled as an idealized battery with a rated EMF, which is shown by this curly E, but it also has a certain amount of internal resistance. And so, when you send an amount of current I through this real battery, the amount of potential drop between C and D is just given by the internal resistance little r times the current I. And therefore, the potential difference that you see across the true ends of the battery is just reduced from the idealized voltage of the battery by an amount given by E minus I times R. Now, this picture out here, and I'll go ahead and erase some of the things that I drew on the figure so that I can actually go ahead and connect the top figure to the bottom figure out here. So let's go ahead and think of a charge that is flowing through this circuit. Imagine that the charge is coming along out here and it reaches the point A. At the point A, we can say that it has some datum amount of energy. Let's go ahead and call that 0. And as it flows through the battery, as it flows through the idealized part of the battery from A to B, it actually acquires an increase in its potential energy and an increase in its electric potential. Okay, then it flows from B to C without any change. However, from C to D, the resistor corresponds to a situation where there's a potential change given by I times little r. So we had a potential rise given by E as we went through the battery. Then across the internal resistance of the battery, we have a potential drop given by I times little r. And then the same current flows from E to F through the external resistor, and that's where it has even the larger amount of potential drop given by I times big R from, so this is the potential drop through the little resistor, and then it flows through the rest of the circuit, and then it flows through the larger resistor, the external resistance, and then it has a voltage drop of I times R. By the time it has come to this point, that's like saying that it has come back to this point out here, so it goes back to this point without change in potential, and it has gone ahead and completed one round through the circuit. In doing so, all the changes in potential up and down must add up to 0. So we have the EMF rise or the voltage rise in the battery, minus the voltage drop in the internal resistance, which is given by I times little r, minus the voltage drop in the external resistance, which is given by I times big R, and that should in fact be equal to 0. This actually allows us to obtain the current flow in the circuit, so we can actually go ahead and say that E is equal to I times little r plus I times big R, and that is actually equal to little r plus big R times I, and that gives us the current I, which is actually equal to the EMF divided by little r plus big R. Okay, so we understand that you don't get all the current that you might desire. In other words, you cannot idealize the situation and say that I is equal to E divided by big R. You'll never get this much amount of current. You will actually get this much amount of current, which is a little less because of the presence of little r, the internal resistance inside the battery. So this actually begins to tell us how very simple circuits might actually be operating. And this actually allows us to plot out the terminal voltage across the ends of the battery. So we realize that the terminal voltage across the ends of the battery is given by E minus I times little r. In other words, you're always getting a little less voltage across the ends of the battery than the rated voltage, as long as you have a non-zero amount of current flowing through the circuit. So as long as you have a non-zero amount of current flowing through the circuit, you will not get the full rated EMF of the battery. You will get a little less because you also have to deal with this internal resistance of the uh, battery itself. So with this idea, or with this understanding, we understand how the external resistance and the internal resistance will interplay with each other. And that actually allows us to come down to this issue, which is to say that we can now start talking also about the power in the battery. So we realize that we had E, the voltage change as charge flowed through the battery, being equal to I times little r, the voltage drop as you pass through the internal resistance, plus I times big R, the voltage drop as you pass through, or as the charge passed through the external resistance. And that actually allows us to obtain the current in the circuit. So I is just equal to E divided by little r plus big R. Okay? We're referring, of course, to the circuit that you saw two transparencies ago. Now, we can actually go ahead and say how much power is delivered by the battery per se. The answer is that the idealized power delivered by the pure idealized battery is just given by I times the rated EMF of the battery. However, what is the power drained in the two different resistors that make up the circuit? So we have an internal resistor in the battery itself, which drains an amount of power given by I squared R. That is just our application of the formula. Namely, the power drained by a resistor is just given by the resistance times the current squared. And then we have an external resistor, which drains an additional amount of power. So we go ahead and say that the power delivered by the idealized battery was given by the previous formula. The power drained by the resistors in the circuit is given by this formula. And of course, we can say that the power supplied, which is I times E, is equal to the power drained in the internal resistor, which is I squared times little r, plus the power drained in the external resistor, which is I squared times big R. Now notice that I can actually cancel off a factor of I on all sides, okay, and I wind up with the same formula. E is equal to I times little r plus I times big R that we had before. That's this formula that we had before. So realize that talking about power is equivalent to talking about the voltage changes in the circuit as we go through that circuit. So power refers, of course, to the time rate of change of energy. The voltage actually refers to just doing a book tracking uh, 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 keeping track of the voltage changes in the battery. And we actually now understand that the two concepts for simple circuits are completely equivalent. So we also understood that a real battery does not supply a constant current, because as the amount of external load that you put on the battery changes, it actually supplies a current that is determined not just by the external load but by the internal resistance also. Okay? And also, a real battery does not supply just a constant terminal voltage, because we realized that the real battery will supply its idealized terminal voltage minus I times little r, where I is the current flowing through the circuit and R is the internal resistance of the battery. So we understood that we will get always a little less than the rated voltage on the battery, simply because there's an internal resistance in the battery. So in the next chapter, we will actually sharpen these concepts, understand how to analyze circuits in various ways, but this was a good introduction. So this is a very simple chapter. It has just a few elements and a few new concepts introduced, but I'll go ahead and thank you all very much for your attention, and we'll sharpen up these concepts in the next chapter. So thank you very much, and see you all soon. Thanks a lot. Bye-bye.